Alright, this video is about shielding and nuclear charge. First thing we want to do is be able to identify what these terms mean. We're going to go ahead and start with nuclear charge. So the first definition would be nuclear charge, okay, an attractive force between the protons, which are positive, okay, that are found in the nucleus, and the electrons that are in the energy levels. Now the electrons are negative, the protons are positive, the opposites attract each other. So usually what this means is different elements are going to have different amounts of nuclear charge. Okay? The more protons that you have in an atom or in an element, the greater the nuclear charge. Okay? So a good way to look at this is so if here's your periodic table. Okay, right? Okay, nothing too fancy, right? So there's your periodic table. Okay, your nuclear charge is going to increase as you go from left to right, okay, because you're going to have more protons as you go from left to right, and it's going to increase as you go down because you're going to have more protons as you go down a group. So they increase, nuclear charge increases as you go down a group, and it increases as you go from left to right. Now this nuclear charge is the driving force behind shielding. Okay, and shielding is when you have the inner electrons or the core electrons, they shield the outer electrons or the valence electrons from the attractive forces of the nucleus. Now, I'm going to show you what that means. Okay, so here I have this one red valence electron right here. Okay, that's in the outermost energy level. Okay, all the blue are your core electrons. Okay, and then of course your red one is your valence electron. Well, the attractive forces between the electrons that are closer, okay, so these electrons, these core electrons, are closer to the nucleus. Okay, so they're really attracted to the nucleus here, right? This electron right here is also being attracted to the nucleus, but we have a little competition going on. Okay, let's go ahead and zoom in on this relationship right here. I have one, let's go ahead and make it a blue line because it's pretty much represent those electrons are moving around. These are core electrons. And then you have this one lone electron out here. Now, this electron is attracted to the nucleus. Okay, so it wants to go in here. But remember, all electrons are negatively charged, and the same thing that, or the same reason why protons are attracted to neutrons, or protons are attracted to electrons repel each other. So these electrons that are in this energy level, this blue energy level, which indicated with all these little blue dots, they are negatively charged. This electron right here is negatively charged, so it's actually pushing back against that valence electron. And it actually shields it, okay, and it produces a little, okay, now that does not form a literal shield like that, but it's preventing that valence electron from getting closer and closer to the nucleus. Okay, so shielding is, in many cases, the reason why atomic radius and ionization energy have their trends. Okay, so your shielding is going to be the reason. Okay, so let's go ahead and take a look at why shielding affects your ionization energy. Okay, so here I got a diagram showing your group. So I'm going down a group right here, and I'm going across a period right here. Now I'm only going one tile over for each, but you'll still see the trend. So this is how ionization energy is affected by shielding. Okay, so as you go down a group, okay, so we're looking at lithium and sodium right here. The more core electrons you have, the farther that outer electron is going to be pushed away. Okay, so ionization energy is going to decrease as you go down a group. And the reason is for the sodium, okay, looking at the sodium right here, electron a little neater, okay, this sodium right here, these 8 electrons that are the core electrons, there's more electrons pushing this red electron away, this valence electron. So the more it gets pushed away from the nucleus, the less the nucleus can pull on that electron, which means it doesn't take much energy to remove that electron. Okay? Lithium, Okay, if we look at its core electrons, right, there's only 2 electrons there, which means the core electrons, there's not as many negative charges shielding this this red valence electron right here. So it is a little closer to the nucleus than this valence electron. Lithium's valence electron is closer to the nucleus than sodium's valence electron is, and that's why lithium would take a little more energy to remove that electron, because it's a lot closer to the nucleus, which means it's more attracted to that nucleus. It takes more energy to remove it from the atom. Okay, so this is why ionization energy, or the energy to remove this electron right here, okay, that energy to remove that electron is much less in with more core electrons, because there's more shielding. The more shielding, then the harder it is for the nucleus to hold on to that electron. Okay. Now, when it comes to going across a period, there isn't necessarily shielding going on, because it's the same number of core electrons. Yeah, I still have 2 core electrons right here, okay, and I have 2 core electrons right here in the lithium. So shielding, for the most part, in a period does not affect or does not have an effect on periodic trends. Okay, the reason why your ionization energy is less in your, say, lithium than in your beryllium is because beryllium has more protons. Okay, so ionization energy is supposed to increase as you go from left to right. Well, beryllium, the reason why it is because beryllium has more neutrons, which causes has more protons, which causes these electrons to want to be closer to the nucleus. Okay, so the stronger the nuclear charge, okay, the nuclear charge is stronger in beryllium than it is in lithium. That's why beryllium it's harder to remove beryllium's electrons, because they're closer to the nucleus. And if you notice, the same reasoning can kind of go with the size and the atomic radius. Okay, so if we look at atomic radius, it's really the same idea. Okay, if I go down a group, okay, so I'm going from lithium to sodium, the electrons are farther away from the nucleus, and the reason why they're farther away from the nucleus is going to be the more shielding that's going on. So there's more shielding going on in sodium than there is in lithium. So as they're being pushed away, that valence electron is getting farther and farther away from the nucleus, which causes the atomic radius to get bigger. Okay, then compared to lithium, there's not as much shielding going on, so the lithium nucleus isn't being as shielded from the valence electron as the sodium's valence electron is. Okay, with beryllium, again, there's not much shielding going on, but the reason why the atomic radius gets smaller as you go from left to right is because these valence electrons, okay, this guy right here and this guy right here, okay, get a pen, this guy right here and this guy right here, the reason why they're closer to the nucleus is because of a greater nuclear charge, or a nuclear attraction, that nuclear charge between the outer electrons and the nucleus. Okay, just to kind of give a example of what a whole group would look like when it comes to shielding, we'll go ahead and look at the alkali metals. Okay, so here we have lithium. This is sodium. This is potassium. This is rubidium, and this is cesium. Okay, so this is as I'm going lithium, sodium, potassium, rubidium, cesium, that's going down a group. Okay, as you can tell, there's more. So if you look at lithium, there's only one set of, because these red dots are not representing the nucleus. Okay, they're representing the core electrons. Well, there's only, in this case, a fewer number of core electrons in lithium than there is in sodium. Okay, and then there's more core electrons in potassium. And there's even more in rubidium and even more in cesium. So the more protons you have, the greater the nuclear charge, but also the more core electrons you have, the greater the shielding, which causes, as you can tell, the radius to get bigger. And because these electrons are now farther away from the nucleus, they're also easier to remove than the element above it.